Lumen point. Let's begin the breakdown.
Quantum computing, man, it can be super confusing, right? But what if the key to understanding its real power isn't about some kind of magic, but actually a really clever geometric shortcut? So today, we're going to cut through all that hype and see how a quantum computer really finds that needle in a digital haystack.
I'm sure you've heard this idea before, right? That a quantum computer can somehow check every single possibility at the exact same time. And yeah, that sounds amazing, this idea of massive parallelism. But as we're going to see, it's actually kind of misleading.
Okay, so let's really think about that. If it can check everything all at once, what does that actually mean for solving a real problem? Like, do you just get the answer instantly? Let's put that powerful idea to the test.
All right, to really get to the bottom of why that summary is so tricky, we're going to frame this whole thing as a quiz. And it's based on a classic computer science challenge, the unstructured search problem.
All right, let's break this down. Imagine you've got this digital lock, maybe with 1 trillion possible combinations. You can punch in any combination you want, and a machine just tells you yes or no. And every single one gets a no, except for one secret key that gets a yes. And your job? Find that one key. The only tool you have is to just try them one by one.
So on your laptop, a regular classical computer, you really have no choice. It's just guess and check. If there are n possibilities, on average, you're going to find the key after checking about half of them. The more combinations, the longer it's going to take. This is what we in computer science call ON time. Basically, the time it takes grows step for step with the number of things you have to check.
Okay, so this is the big question, right? If that whole checking everything at once idea is true, how much faster can a quantum computer nail this? Is it just one shot? Or something else entirely?
You know, when this exact quiz was given to thousands of really smart people, we're talking Stanford students, Math Olympiad competitors, most of them got it wrong. Yeah, the number one answer by a long shot was 01, just one single step. And that guess comes directly from that misleading checking everything at once idea. The next most popular answer was also wrong. The real answer is much more interesting.
But the real answer? It's O of the square root of n. So for that list of 1 trillion items, you don't need 1 trillion steps, or even half a trillion. You just need the square root of that, 1 million. Now that is a huge speed up, but it's definitely not instant. So where in the world does this square root come from? To get that, we have to kind of toss out our old mental model and build a new one.
Okay, so let's do it. Let's throw out that old summary. We're going to build up a much more honest and, frankly, cooler picture. And it's all based on a few strange but totally true rules about how these quantum systems actually work. First thing, forget about bits being just a 0 or a 1. The state of a quantum computer is described by something called a state vector. And for our purposes, just think of it as a big list of numbers, or scores. There's a score for every single possible answer to our search problem. And the higher the score, the more likely it is that we're looking at the right answer.
Now this is where things get really weird. You can't just look at the state vector and read off the answer. No, instead, the probability, the chance, of actually seeing any one answer when you measure the computer is the square of its score. It's a bizarre but fundamental rule of quantum mechanics. Probability equals the score squared. Okay, let's make this simpler. Think about just one quantum bit, or what we call a qubit. You can picture its state as an arrow on a circle. The more that arrow points horizontally, the higher the chance you'll measure a 0. The more it points vertically, the higher the chance of a 1. And really, at its core, a quantum algorithm is just a super clever way to rotate that arrow so it points right at the answer we're looking for.
Okay, so how does all this geometry stuff connect back to Grover's amazing algorithm? Well, it's not about parallel processing. It's actually this beautiful two-step geometric trick for rotating that state vector, that arrow, and pointing it directly at the answer.
Yeah, you can really think of it as a two-step dance. Step 1, we use this thing called an oracle, and you can think of it like that digital lock from earlier. It knows the secret key, and when it finds it, all it does is it flips the sign of that key's score in our big list of numbers. Step 2 takes that entire vector and reflects it around the average of all the scores, and then we just do it again. Repeat.
And here, this is the geometric magic. It's a neat little trick from geometry. If you do 2 reflections, back to back, what you get is a rotation. So every time we do this two-step dance, we aren't just flipping things around randomly. We are precisely rotating our state vector, inching that arrow just a little bit closer to the right answer. So here's where the math really clicks into place. We start out in this balanced state, right? The arrow is pointing in a direction that's just the average of everything.
Now, the angle between where we are and where we want to be, it's super, super tiny. But each one of those two-step rotations moves the arrow a little bit closer. And it just so happens that to rotate that arrow all the way to our target, you have to do this dance about, you guessed it, the square root of n times. And boom, there it is, our O of root n speedup. It's not magic, it's geometry.
So this gives us a way better mental model, right? A much more accurate one. Quantum search isn't about checking all the paths at once. It's about having access to a shortcut, a direct path through this incredibly complex, high-dimensional space. A shortcut that classical computers just can't take.
This is the perfect analogy. A classical search is like trying to get to the opposite corner of a cube, but you're only allowed to walk along the edges. You have to take all n steps. But a quantum search, it lets you cut straight through the middle, right across the diagonal. That path is way shorter. Its length is the square root of n. See? You're not checking every single path at once. You're taking one path. It just happens to be a much, much shorter one.
And this whole geometric view, it creates this fascinating tension that's really unique to quantum computing. With every one of those little rotations, our chances of getting the right answer get better and better, but it's never a sure thing until you get to the very end. So just imagine the stakes are impossibly high. Do you take the measurement now and risk it all on a probability? Or do you let the algorithm run just a little longer, hoping you have enough time to get closer to that perfect certain answer? It's a question of probability, risk, and the strange, powerful geometry of the quantum world.
Fuel your curiosity. Subscribe for the explanation. Stay for the knowledge.